We're looking at the Math 136 Chapter 12 Chapter 12 review activity, which is a review of the unit on probability. Okay. The first one deals with access codes for a security system. So it says the access code for a car security system consists of 4 digits. Each digit can be 0 through 9, so there's 10 choices there. How many access codes are possible if each digit can be used only once and not repeated? Okay, so I like to call this my slot and choice problems, where we have 4 slots because the access code consists of 4 digits. Okay, and then for the first slot, right, for the first digit of the access code, we're going to have 10 choices. And then, since we cannot repeat the digits, for the second digit we only have 9 possibilities. And now we can't repeat either of those two, so now for the third digit we only have 8 possibilities. And now for the fourth digit we only have 7 possibilities. And it's really a counting principle problem, right? And counting principle says that you just multiply all these numbers together, and when you multiply 10 times 9 times 8 times 7, we get 5,040. So there's 5,040 possible access codes if each digit can be used once and not repeated. Okay. Now, if each digit can be repeated, it's actually a simple problem. It's still the same setup. We have 4 slots, right? One for each digit of the access code. But now, since we can repeat digits, we're going to actually have 10 choices for each of these slots. And again, by counting principle, we're just going to say 10 times 10 times 10 times 10, which is going to be 10,000. Right? So there's quite a bit more possibilities if you can repeat the digits than if you can't. There's almost double the amount of possibilities. Okay, so that was really a counting principle problem. Now, number 2 says 2 cards are selected without replacement. Right, without replacing the first card from a standard deck. Find the probability of selecting a king and then a queen. So the way that I would write this out would be the probability of K and then Q. And we had a multiplication rule for this, which said the probability of A and then B is going to be the probability of A times the probability of B, but in this case A and B are really king and queen, right? So I'm actually going to have the probability of the king times the probability of the queen. And of course there's 4 kings in the deck of 52, so the probability of getting a king is 4 out of 52. And now this is where you got to be a little careful, because I'm drawing 2 cards without replacement. So now when I draw my second card, I only have 51 possibilities left. And out of those 51 possibilities, there's 4 queens in there. So I would just multiply this, and I would get 16 out of 26, 52. Which you could reduce if you want to, but I would just leave it in this form. Okay? And then 3 is the same kind of problem. It's an and then problem. Okay, I think we did a similar one on my handout. Right? If you toss a coin and then roll a die, what's the probability of getting a head and then rolling a 6? So it's similar to the last problem. So in this case, it would be the probability of heads and then 6. But it's the same formula. It's still our multiplication formula. So this would just be the probability of heads times the probability of a 6. right? And on a, with a coin, the probability of getting heads is just 1 out of 2, right? It's either heads or tails. And on a die, the probability of getting a 6 is 1 out of the 6 choices, okay? So it's a half times 1/6, which would just be 1/12. So that's 1/12. And then 4 is just kind of a explanation question dealing with mutually exclusive. Now, if you remember, what mutually exclusive meant was they had no outcomes in common. So in this case, 25% of these patients had high blood pressure, 50% were overweight, and 15 had both. So whenever there's a certain percentage, or some people in this case that had both high blood pressure and were overweight, we would say the events are not mutually exclusive, right? So are the two events mutually exclusive? No, because there are patients, specifically 15% of the patients, who have both conditions, right? Now, if there weren't any patients that had both, they would be mutually exclusive events, right? But in this case, there's 15% that have both, therefore they're not mutually exclusive. So that's really just a definition question, really. Okay? And then they say if one of the patients is selected at random, what's the probability that the patient has high blood pressure or is overweight? So this was the other formula, right? In the first couple problems, we dealt with that multiplication formula. This is actually the addition formula involving or, right? Which the general form was the probability of A or B is going to be the probability of A plus the probability of B, and then minus the probability of both A and B. So in this case, think of A as the high blood pressure and B as the overweight, right? So it said 25% had high blood pressure and 50% were overweight. So the probability of high blood pressure was 0.25. The probability of being overweight was 0.50. And then I'm subtracting the probability that they had both conditions, which was 15%, which was 0.15. So I would add these up. I'd have 75% minus 15%, which is going to be 0.60. Right? Or 60%. So the probability that they have high blood pressure or are overweight is 60%. Alright? Now, 5, Rita is playing 3 tennis matches. List the sample, it should say list the sample space. There's a little error there. List the sample space with the possible win and loss sequences that she can experience for this set of 3 matches. Well, I mean, you can do a tree diagram if you want. So the idea is if you're playing 3 matches, you have like 3 different levels. You have a level for match 1. So match 1, she can either win or lose. Then you have a second level for match 2, where she can win or lose the second match after winning or losing the first match. And then you have a third level for match 3, oops, not MS, M3, where each of these would have a win and a loss coming off of it. And then what you do is to list the sample space, you look at all these end leaves, we'll call them, right? And trace them back to where they came from. So this first one came from www, not World Wide Web, right? Win, win, win. This one came from WWL. This one came from WLW. This one came from WLL. And now I'll create a second column. This one here came from LWW. This one was LWL. This one was LLW. And this was LLL. So we have 8 possibilities here. And is this an equally likely sample space? Well, it's kind of a trick question. I mean, I would probably say yes. And the answer is yes. But we're really assuming there's a 50% chance of Rita, so her, winning each match. Right? If she's a really good player, maybe she has a higher than 50% chance of winning each match. So maybe if she's a really good player, she'd have a higher probability of winning. If she's a poor player, maybe she'd have a lower probability of winning. But it's equally likely, assuming that there's a 50% chance of her winning each match. Okay? And then 6, this isn't a very long review activity here. There's not many problems. I'll make another video shortly. Well, not today probably, but maybe another day where I do the some of the review sheet problems, because this isn't really enough. So 6 just says, explain clearly the difference between a combination and a permutation. Really the difference is, and I think I had written it in class, a permutation is an ordered arrangement. Right? And the key word there is ordered. I mean, really, ordered and arrangement both kind of imply the same thing. Arrangement kind of implies that there's an order involved, right? So permutation is an ordered arrangement of objects, whereas a combination is more like a selection of a certain number of objects. And the key with combinations, of course, was that the order wasn't important. So whenever order was important, you were really using a permutation, whereas when order wasn't important, you were using a combination. Right? So permutations are ordered arrangements, whereas combinations are just really selections or choosing of a certain number of objects where the order plays no role. Okay? So then the question is in B, New Jersey has 14 four-year colleges. Diana wants to apply to 3 of them. In how many different ways can she select? And actually, it's nice that I use that word selection there for combinations, because that kind of gives it away. In how many different ways can she select 3 colleges to apply to? Now, they're not saying that she has a first choice, a second choice, and a third choice. We're just saying she's selecting 3 colleges out of these 14. So this is really a combination, because she's just selecting. The order isn't important. So what you're really doing here is what's known as 14C3, which you could do on a calculator. And if I do it on the calculator, I would just enter 14 NCR 3, and I would get 364. So it's 364. If you don't have that button on the calculator, remember how to find the combination. It's 14 times 13 times 12 over 3 times 2 times 1. And that will give you 364.